forward the entire screen, please. There we go. Okay. So today, so the basic idea is the following, that say we have some random variable, we'll assume a real valued random variable for simplicity, we assume it has some associated CDF, and then it's fairly straightforward to show that if you take a transformation of the random variable, define a random variable y that's some arbitrary function of x, that's also going to be a random variable. Just like a simple example, say like x is normal, we want to find the distribution of x squared. Well, that's also a random variable, and this new random variable is also going to have some sample space that's going to be some subset of the real numbers. Basically, most of today's lecture is going to focus on how do we find the CDF of this new random variable that's a function of the previous one. So, simple example, let's say we have an exponential random variable that I described briefly in the previous lecture, and that has cumulative distribution function 1 minus e to the minus x, and density function e to the minus x. Let's say we create a new random variable that we define to be y divided by, y, which is equal to x divided by some value lambda. Well, the simplest way to figure out what the CDF of y looks like is just use the formula for the CDF. F sub y of y, by definition, is the probability that big Y is less than or equal to whatever this little y is. And in this case, big Y we define to be x divided by lambda, so that's just going to be the probability that x is less than or equal to lambda times y, which of course is equal to what we would get if we just plugged lambda y into the CDF for x. And we end up with the CDF for y being equal to 1 minus e to the lambda y, exactly the same as the CDF for x, except now the x is multiplied by lambda. And little aside, this is defined to be exponential random variable with rate parameter lambda. We say you can easily show through differentiation that the density function will be lambda e to the minus lambda y. This is one of the properties of an exponential, that if you just divide it by something, you end up just changing the rate of the variable, which makes intuitive sense if you're talking about the rate that the number of failures occurs or something like that. Then if you divide, say, minutes into seconds, then that should just increase or decrease, or it should affect it by a factor of 60, and that should be a simple calculation, but it's not so simple when you're in a room full of people and you haven't slept, but you get the idea. So, simple example of this. Say we're changing units from Fahrenheit to Celsius. Presumably, you've all seen this formula before, that if you want to convert Fahrenheit to Celsius, you take the temperature in Fahrenheit, subtract 32, and multiply it by 5/9. So if we had some random variable that was defined in terms of Celsius in the range 20, and this particular random variable, the room never goes outside of a temperature between 20 and 30 degrees, for instance, that would be the range of the random variable y prior to the transformation. After the transformation, the range would obviously go from 68 to 86. So basically what we're trying to do today is, given some random variable and give some transformation to another random variable on some units, what would be the new cumulative distribution function and the new set of measurable sets and so forth for this new random variable. So how do we define this new random variable exactly? Well, y here once again represents the new random variable, and to define this random variable y, we have to define the probability on any possible Borel set. So the probability that y is in some given Borel set is obviously the probability that g of x is in that Borel set, which, if we go back to the original sample space, recall that the random variable is just a map from the sample space to the real numbers. It's the set of x's in the original sample space such, I guess I shouldn't say the original sample space, this is actually the real valued sample space for random variable x, not the sample space for the underlying process of interest. We want to find the real valued sets x, the set of Borel sets, such that g of x is in A, and that's equivalent to saying we want the x such that the probability of the x's that are in the inverse image of g of A. We define this inverse image to be the set of x's precisely such that g of x is in A. And you can define this even if G is not necessarily a one-to-one mapping. That, for instance, if g of x equals x squared, for instance, the set of x is such that x squared is between minus 1 and 1, is once again between minus 1 and 1, even though x squared is not a one-to-one map within this range. If that's confusing, hopefully it'll make more sense as I go through some more examples. In principle, we can do these transformations for discrete random variables as well. That, say we have some discrete random variable with some probability mass function, and say we have a one-to-one transformation g of x, then to find the probability mass function for g of x, then we just sum over all the x's such that g of x equals to y. And in real life, pretty much nobody ever does this because it's usually completely straightforward to do. So honestly, I doubt you'll ever see this again. I'm not sure I ever even thought about this before I prepared this lecture because it's honestly quite trivial. It's the continuous case where things are a little bit more exciting. For now, let's make our life easy and let's assume that g of x is a strictly increasing function, hence it's a one-to-one transformation, and let's also assume that g is differentiable. So this means that we can define that an inverse function for g inverse exists. And to calculate the cumulative distribution function for this derived variable y, we can just define it in terms of the inverse function for g, similar to the logic that I used earlier, the probability that y is less than or equal to y, the probability that g of x is less than or equal to y, and since g is invertible, that's just the probability that x is less than or equal to g inverse of y. So then, to calculate the cumulative distribution function for y, you just take the cumulative distribution function for x, and plug in the inverse function of the inverse of whatever your transformation function is. And to calculate the PDF, it's similar logic, only it gets a little bit hairier. We have the formula for the CDF now. To get the PDF, in general, you just differentiate the CDF, and so what that boils down to, if you remember back from when you took calculus, hopefully not too many years ago, this whole chain rule thing, honestly had to remind myself of this myself, but in general, the chain rule says that if you're differentiating an f of g of x, then the derivative is going to be f primed of g of x times g primed of x. So in this particular case, we're differentiating f sub x of g inverse of y, so that's going to be f primed of g inverse of y times the derivative of g inverse. So f primed of x, that's just the probability density function for the original variable x, so that's fairly straightforward to calculate. We just take the density function for the original f and make that and plug in g inverse of y inside of that. Then we have to multiply by the derivative of the inverse of the transformation function with respect to y. It's kind of hairy in terms of math, but if you remember how to take derivatives, which I know is a dangerous assumption if you're like me, but hopefully we can all remind ourselves how to do it. It's just differentiation and multiplying things together. It's not that hard conceptually. And now let's make this a little bit more complicated. The g of x is still a one-to-one mapping, but it's decreasing instead of increasing. So in this case, we want to find the probability that g of x is less than or equal to y. Well, since g is a decreasing function, that's equivalent to the probability that x is greater than g inverse of y. We reverse the direction of the inequality here because it's a decreasing function, and that's of course just equal to 1 minus the CDF of x evaluated at g inverse of y. So to get the density function, we differentiate that thing again, and same sort of thing, f primed of g inverse of y times g inverse primed of y. We end up with minus 1 times the density function of x evaluated g inverse of y times the derivative of the inverse of the transformation function, which is just going to be equal to the density function of x evaluated at g inverse of y times the absolute value of the derivative of the inverse function, because since the transformation function is decreasing, its derivative is going to be negative, so this sign is always going to be negative and it'll cancel with this, so if we just put the absolute value there rather than minus 1 times the derivative, we end up with the same thing. So this allows us to simplify the formula a little bit, that if the mapping is 1-to-1, regardless of whether it's increasing or decreasing, as long as it's monotonic, then the formula for the PDF of the transformed variable y is just the PDF of the original variable x evaluated at the inverse function of y times the derivative of the inverse of the transformation function. Oh, if you're completely lost at this point, hopefully it will be a little bit clearer after I do a couple examples. So, simple example here, let's say that y is just a linear transformation of x. We multiply x by some constant b, add some constant a. Obviously, the derivative in that case is just equal to b. So, if we plug in the formula for the density function from the previous slide, I should have pointed out that to calculate g inverse of y in this case, that's just going to be x equals y minus a divided by b. Hopefully the algebra there is straightforward enough. So the formula for the distribution function of y is, once again, the distribution function of x evaluated at the inverse of y, which in this case is y minus a divided by b, and then multiply that by the derivative of the inverse of the derivative of the inverse with respect to y. In this case, once again, the inverse is y minus a divided by b, so the derivative will be 1 over b, and we can say absolute value so we don't have to do special cases depending on whether b is positive or negative. And if you've taken basic statistics in the past, this transformation comes in handy when you want to create a new random variable that has the same shape of x but has given mean and standard deviation. It's most commonly used with the normal distribution, that the old trick that if you have something that's normally distributed with arbitrary mean and variance, you subtract off the mean, divide by the variance, and you end up with something that's normally distributed with mean 0 and standard deviation 1. Here is the formal derivation of that. In fact, I'll show this example in more detail in the next slide. And yeah, I guess I basically already said this, that in general, that if you take some arbitrary random variable, subtract mean divided by the standard deviation, you get something with mean 0 and standard deviation 1, sometimes known as the studentized transformation. So, special case of the normal distribution, my guess is many, if not most, or all of you have seen this before. If not, we'll be covering it in more detail here in a bit. But we'll assume x is normally distributed with mean 0 and standard deviation 1. So let's do a transformation where we multiply x by sigma and then add mu to it. It's equivalent to giving this particular normal distribution a mean of mu and a standard deviation of sigma. Obviously, the inverse transformation here is y minus mu divided by sigma. So, if we calculate the density function for x, that will be the density function for y, that will be the density function of x evaluated at y minus mu divided by sigma times the derivative of this expression for x here, which is of course 1 over sigma. And we end up with 1 over square root of 2 pi times sigma times e to the y minus mu squared over 2 sigma squared, which, if you're familiar with the normal distribution in the past, you recognize as the density function for a normal distribution with mean mu and standard deviation sigma. And quick aside that if the distribution, any distribution such that if you do a linear transformation of the variable, you get the same distribution but with different mean and standard deviation or different parameters generally, that's known as a location scale distribution. The normal distribution being far and away the most famous example. There's a couple other distributions that have this property that you'll use from time to time. So, just to do a more complicated example that will end up with something that you won't see as often, like the square root of an exponential random variable. In the simple example I showed earlier, we saw that if you do a constant times an exponential random variable, you end up with another exponential random variable. So this time, let's make it a little more complicated, and let's take the square root of an exponential rather than just multiplying it by a constant. So the transformation function here would be y equals the square root of x. It's a one-to-one mapping, and its inverse is obviously going to be x equals y squared. The derivative of that with respect to y will be 2y. So that implies the density function for this new variable y. It will be just the density function of the original random variable x evaluated at y squared times 2y. So if we substitute y squared into the density function f of x up here, we end up with 2y times lambda times e to the minus lambda times y squared for y greater than or equal to 0. And apparently this is a particular form of the Rayleigh distribution, is a special case of some other distributions that, quite honestly, if I've ever heard of these distributions before in my life, I forgot about them. So I don't think you will probably need to know about this either, unless I or some sadistic future instructor writes a homework problem about one of them. But one case of transformation of random variables that actually is quite useful in practice is what's known as the probability integral transformation. That, let's say that x is some random variable and it has some cumulative distribution function. So that we call f. So let's define a random variable y to be f sub x of x. So in other words, we're taking a random variable, plugging it into its own cumulative distribution function. Here, just for the sake of simplicity, we'll assume that the distribution function is strictly increasing, so its inverse exists. There's ways to do it when that's not the case, but it's a lot hairier, and it's not commonly done in practice, so I'm not going to worry about it. So, in this case, if we take the derivative of the inverse, if we take the derivative of x with respect to y, or the derivative of y with respect to x, sorry, got that backwards, that's just going to be the derivative of the CDF of the original x, which of course is just the density function for the original x. So to get the density with respect to y, then you take the density with respect to x evaluated, I think that's a typo, I have to double check that. I mean, I just mindlessly copied the slides without thinking, or no, I guess maybe that's not a typo. That boils down to the density function of x evaluated at the inverse of the CDF evaluated at y, divided by the same thing, you end up with 1. In other words, if you do this transformation, you end up with a random variable that's uniform over 0, 1. which, if you think about it for a minute, it kind of makes intuitive sense that if if you plug a variable in the CDF, by definition, is the probability that the random variable is less than or equal to a certain number, and which will be some probability between 0 and 1. So if you take any random variable, plug it into its own CDF, and find the CDF of that, it's going to be a number between 0 and 1, and it's equally likely to be any number between 0 and 1. And perhaps an easier way to see this is just to look at the original distribution function itself, that the distribution function of the derived variable y, by definition the probability that y, big Y, is less than or equal to some little y, which is the probability that the CDF is less than, or CDF of x is less than or equal to little y, which is the probability that x is less than or equal to the inverse of the CDF of y, which is the definition of the CDF of the original x. So you have the CDF with respect to x evaluated at the CDF of x inverse. You end up with y as the CDF, which is just the CDF for the uniform distribution on 0 to 1. So why do we care about this? Well, in principle, you could use this for evaluating the goodness of fit of a distribution to a data set. That if, for example, you have some random variable that you believe to be exponentially distributed, so you plug it into its, so you take this random variable x, or to be more precise, that you believe to be exponentially distributed with rate parameter lambda, you plug in, so you take the x, multiply it by minus lambda, take 1 minus e this, and that should be uniform on 0 to 1. And so then you transform these data points into something that should be 0 to 1, and see, it should be uniform on 0 to 1, and see if it actually is uniform on 0 to 1. I mean, this is the basic idea behind when you do QQ plots to see if two distributions are the same, if you've ever done that sort of thing before. And another place where this probability integral transformation is sometimes used is if you go in the backwards direction, that you take a bunch of numbers that are uniformly distributed between 0 and 1 and then do the inverse procedure. That, say, for example, let's say let x be uniform on 0 to 1, I guess I should have clarified sooner, that x uniform to 0, 1, if you haven't seen that before, this means x is equally likely to be any number between 0 and 1. It's hopefully a reasonably straightforward distribution. And it's fairly easy to show if x is uniform on 0 to 1, then its density function is just 1 on the interval from 0 to 1, and its CDF is x on that same interval. So if you define a random variable y to be f inverse of x, where f is just the distribution, the CDF for some distribution, then it's fairly easy to show that the distribution function for y is going to be just the integral from minus infinity to y of f sub x dx, which is precisely the definition of the CDF for a random variable with distribution function y. Similarly, we go through the math here, we show that the distribution function, or the density function for this new y that we just defined up here is just f, whatever the density function is corresponding to this distribution. So you can, if you go, it's maybe easier to see if you go through the distribution functions here, that if we want to find the cumulative distribution function for this new random variable y that we defined up here to be the inverse of some CDF, that's the probability that this new y is less than or equal to y. It's the probability that f inverse of x is less than or equal to y, which, of course, the probability that the uniform distribution x is less than or equal to f of y, and since the CDF of the uniform distribution is just x, that's just equal to f of y. So in other words, if you take something that has if you generate a bunch of variables that have a uniform distribution and then plug them into the inverse CDF of some distribution, what you will get out of that will have whatever that distribution is. So the reason you would care about this is if you're trying to simulate random variables that have some distribution. That most computer random number generators are designed to generate random numbers between 0 and 1. If you've ever done any programming before, you know that most random number generators just generate random numbers in that interval. And people have spent a lot of time and energy trying to figure out algorithms for generating random numbers between 0 and 1. Well, what if you don't want random numbers between 0 and 1? What if you want to generate a bunch of normal random variables, or a bunch of exponential random variables, or, heaven forbid, generate random numbers from the surface of an n-dimensional sphere? I actually had to do that on a research problem the other day. But if you want to generate random numbers satisfying some funky distribution, then you can use this probability integral transform. Simple example here, say we want to generate random numbers that have an exponential distribution. So we know the CDF of the exponential distribution is 1 minus e to the minus lambda y. So we invert that. The inverse of that pixel function is minus 1 over lambda times log of 1 minus x. To generate random numbers having an exponential distribution, that we can generate random numbers that are uniform in 0, 1, plug them into this formula here, and you will end up with random numbers that are exponentially distributed with rate parameter lambda. And as I already said that, and this is worth remembering because it is actually useful sometimes if you're ever doing research or and you need to generate random numbers satisfying some strange distribution. I mean, obviously, I don't know if you've ever had to do something like this before at this stage in your careers. If you just need to generate something simple like normal random numbers or exponential random numbers or whatever, R will do this for you, although my understanding is if you look under the hood of R is doing precisely this. But if you need to do like what I did and generate random numbers from the surface of an n-dimensional sphere, R isn't going to do that. So in that case, you need to figure out the distribution function for whatever distribution you're trying to sample from, invert it, and then generate uniforms and plug it into the inverse of that distribution function. So, lest you think that you'll never use anything from this class again after you pass quals. Wow, not even a chalk off. Yeah, I hope I haven't been too excessively cynical in this class. You're not all just sitting here like, oh, I hate this life, I hate grad school anyway. So, another example of this type of transformation is how you could generate variables from the Cauchy distribution. If you're not familiar with the Cauchy distribution, it's a famous example of a distribution in statistics. It's shaped kind of like a normal distribution, but it has ridiculously heavy tails, orders of magnitude heavier than you would see in a normal distribution. And later on, we may do this in this class, you'll probably see the examples later. But like a normal distribution, if you take a bunch of things, average them together and take their mean, as the number of things that you average gets close, increases, you'll get a normal distribution with smaller and smaller standard deviation, that the mean will get closer and closer to the population mean as your sample size increases. You try that for Cauchy, it doesn't work at all. You take a sample of 100, 1,000, 10 million Cauchys, it's not going to be any closer to the mean than the original Cauchys were, because its tails are just so ridiculously huge. If you've ever taken classes in mathematical statistics before, the Cauchy distribution has infinite variance and actually even has undefined expected value just because its tails are so huge. And if you have no idea what I just said, don't worry about it. I'm going to explain it in a week or two. But just a quick overview of why we care about the Cauchy distribution. It's another thing that you will occasionally use in practice if you're trying to say, what if this data set has ridiculously large outliers, so much larger than you're ever likely to see in practice? You can sometimes simulate data with a Cauchy distribution just to illustrate this is what happens when the data is really badly behaved. In fact, I did this in a paper that I submitted a while ago. So, anyway. So to generate like a Cauchy random variable, say that we're simulating random numbers between minus pi over 2 and pi over 2. You can easily show that the density function would be 1 over pi, in this case for a theta between minus pi over 2 and pi over 2. If your random number generator only generates between 0 and 1, it's easy enough to just do a transformation into that interval. So let's say we do a transformation on these y's, or on these theta, and we call this transformation tangent of theta. Well then, if you remember both calculus and trig, which might be an even more dangerous assumption, I certainly would have had to look this up if it weren't in the slides that I was given, but the derivative of y with respect to theta in this case would be secant squared of theta, which of course I'm sure you remember all the trig identities from high school. If not, then look this up and hope that they don't require you to remember this on an exam. That's equal to 1 plus the tangent squared of theta, which of course is just equal to 1 plus y squared. So if we then, to calculate the density function for this derived variable y, that's just going to be the density function of the original random variable theta, 1 over pi, times the 1 over this derivative, which is 1 over 1 plus y squared, which, if you've ever seen the Cauchy distribution before, that is the density function for the Cauchy distribution. So, like I said, if you ever needed to generate Cauchy random variables to prove that your method works even when the data is really strange, that's how you would do it. I mean, R will generate Cauchy random variables for you, so in practice you probably won't need to use this unless you're programming in C or something like that, but that's how it's done. And now we'll consider the slightly more complicated case of where your transformations are not monotone. let's say that you want to do a transformation that's not one-to-one. The trick here is to start with the CDF of the transformed variable. Like an example, let's say that we have some continuous random variable x. We want to find the distribution of the absolute value of x. So the simplest way to do this is just to write down the CDF for this y and try to write it down in terms of the CDF of x, in which case then you've effectively solved the problem. So in this case, if we want to find the CDF of this derived variable y, that's going to be f sub y of y. That's going to be the probability, by definition, that's the probability that y is less than or equal to y. Well, y is equal to the absolute value of x. So that's the probability that x is between minus y and y. Well, we know how to calculate that, at least in terms of the CDF of the original x. That's just going to be f sub x of y minus f sub x of minus y. So to calculate the density function, all we need to do is differentiate that with respect to y. We end up with f sub x of y plus f sub x of minus y. So even though it's not a one-to-one mapping, using this particular approach, we can still calculate the CDF and the density function of this transformed random variable. So let's say we have a random variable with a normal distribution, and we want to find the distribution of the absolute value of a normal distribution. Then all you have to do is plug it into that formula. In this case, the normal distribution is symmetric, so f sub x evaluated at y plus f sub x evaluated at minus y is just going to be 2 times the density of the original normal distribution. So rather than 1 over square root of 2 pi, it's 2 over square root of 2 pi, but it's otherwise the same. And also, it's only evaluated from 0 to infinity rather than minus infinity to infinity, because obviously the absolute value cannot be 0. And now let's say that we want to find the distribution of y equals x squared. Again, it's not a one-to-one mapping. And in this case, the derivative of x with respect to y would be 2 times x. So or in other words, that would be equal to 2 times the square root of y if we write it in terms of y, or at least the absolute value would be. It's, in general, it's not well defined because it's not a one-to-one mapping, as I said. Oh, if we want to find the distribution function, or the cumulative distribution function for y equals x squared, we can do the same trick that we did with the absolute value. That's just going to be the probability that x squared is less than or equal to y, which of course is equal to the probability that the original x is between minus square root of y and plus square root of y. So to get the cumulative distribution function for y equals x squared, we just take the cumulative distribution function of the original x evaluated at the square root of y minus the cumulative distribution function evaluated at minus the square root of y. And similarly, we can, to get the density function, we just differentiate that. It's a little bit uglier now because we have the square root inside, so we have to use the chain rule, but still not too bad. We just end up with 1 over the square root of 2y times the original density evaluated at y plus evaluated square root of y plus the original density evaluated at minus square root of y. So, example of this that will hopefully make this a little clearer, say x has a normal distribution, we want to find the distribution of y equals x squared. I should clarify standard normal distribution here. Density for standard normal distribution, 1 over the square root of pi times e to the minus x squared over 2. So plugging this into the formula from the previous slide, it would be 1 over 2 times the square root of y times the density of the density of the standard normal evaluated at the square root of y plus the density of the standard normal evaluated at minus square root of y. Maybe I should have written all that out, but one way or another, the density evaluated at the square root of y, we just plug the square root of y into x squared, end up with just y. That's the same for both plus square root of y minus square root of y, hence we end up with 2 times the density, 2 times this density here. So simplify that out, we end up with y over 2 to the minus 1/2 times e to the minus y over 2 divided by 2 times square root of pi. And if you've ever had any classes in mathematical statistics before, you may recognize this as the density of a chi-square distribution. If not, once again, we'll be discussing this shortly. So, and this is, and we'll also discuss later, this is a special case of the gamma distribution, which, unless you've taken a comparable course in another class you probably have not heard of before, don't worry, we'll discuss all of this. Oh, in general, if you want to if you want to calculate the cumulative distribution function and density function for y equals g of x, that's not a one-to-one mapping, but for which you can split your sample space up into a bunch of disjoint sets that span the domain and such that it's continuous and one-to-one within each of these disjoint sets, then the inverse will exist within each of these disjoint sets, and you can find the density function just by basically doing this entire process that we've just talked about on each of these disjoint sets separately and then adding them all together. This is just a fancier way of saying what I illustrated on the previous slide, that you can split your cumulative distribution function up into the different ranges where it's one-to-one, add them all together, and then differentiate that. So, I know that can be kind of hard to wrap one's brain around, and it's not something that I intend to make you do very often, if at all. So, here's one simple example of this. But say that we have some density function that represents a random angle of rotation from the x-axis on the unit circumference in radians. The angle that we observe will just be x modulo 2 pi, because if we observe like a 45-degree rotation, which would correspond to, what would that be, pi over 4, until I remember my trig really well, doesn't matter. But one way or another, you can't tell if you did a full rotation before you got to 45, or 2 full rotations, or 3 full rotations, they all look like you're just at a 45-degree angle. So, all we observe is this final angle modulo 2 pi. So, in this particular case, to find the density function, then you just invert that on every single one of these possible intervals. And if you're in the interval 0 to 2 pi, then you don't need to add anything to it. If you're in the interval 2 pi to 4 pi, then you need to add 2 pi to whatever you observe. If you're in the interval 4 pi to 6 pi, then you need to add 4 pi, etc., etc. So to get this density, you just take the sum over all possible j's so to get the density of this derived variable theta, you just take the density of the original f, shift it by 2 pi units where the shift varies over all possible integers, add all those together. This, I don't know when you would ever do this in real life. This is kind of just an illustration of how this whole process works. So for instance, if x were normally distributed and all we observed was the normal distribution modulo 2 pi, then you could get the distribution of this crazy derived variables by taking the sum of a bunch of normal densities, each shifted by 2 pi units, or some multiple of 2 pi units to the left or to the right. And yeah. That's all I got. Any questions about any of this? At least somewhat clear, hopefully.
I have 2 questions on the probability integral transform.
Mm-hmm. Okay. Oh, sorry.
Yeah, right there.
Okay.
Where did the big F inverse in the denominator come from?
That is a good question. Do I understand my own slides myself? I think.
That's the DXY.
Yeah. That comes from the fact that we have to multiply this by the derivative with respect to whatever the formula is. Geez. You can tell I'm more than a little rusty on this stuff, but it comes from this formula, basically, that you calculate that derivative, and it comes out to be 1 over the density evaluated at F inverse of... it turns out to be 1 over the density function evaluated at the inverse of the distribution function. I can't even say it right. Still not seeing it?
I think it's like the confusion whether that it could just be like absolute value of 1 over f of x of x. Like if you just directly took the thing, the line above the derivative that you did, but you're using f of x.
That's y dy dx.
Yeah.
I think that 1 over thing is just the original dy dx is f x, so that's f x. Big f x inverse of y, and dx over dy is just the reciprocal of that. So it's 1 over f x. max inverse y. So that makes sense.
Yeah. Did you follow that? Don't worry about it too much. This is, I mean, the probability integral transform, I mention it more because it is one of the things from this class that's actually useful, even if all the details of the derivations, I mean, it wouldn't be a terrible exercise to go through this and write down the formula for the transformation generally and convince yourself that this expression is correct. But honestly, it's been so long since I've done this, I'm rusty on this myself, and I'm trying to come up with a simpler way to write down the math myself, and I'm not doing it. If I can try to come back to you with a better answer next week, if you'll give me some time to think about it. I'm sorry that... Are there any other questions about any of this?
Not that I can explain yet.